Okay, welcome back. This is going to be a quick one showing you how to solve the coefficient of friction in a combined force and motion Newton's laws style problem. What we're going to look at here is we're going to have a 50 Newton force pulling a 2 kilogram block at 3 meters per second squared across a sheet of sandpaper. Draw a free body diagram or force diagram showing all the forces acting on the block, along with any values that you know. Determine the value of the coefficient of friction. I view this problem as a kind of a working in reverse style problem because when I start to teach this, I provide the coefficient of friction in the problem. The students are able to calculate the frictional force, and then they're able to determine if the object is able to move, and if it does, if it accelerates. We're going to work backwards on this, and I'm going to start you off with the acceleration rate and have you work to figure out what is the frictional force that causes this to happen, and then we'll use the friction equation to calculate the actual roughness of the surface, the coefficient of friction. Let's just lay this one out. So it doesn't have to be super fancy, but so there's my block. Mass goes in the middle for me. It is on a surface. So there's going to be a mu hanging out over here. I don't know what it is. I do know that the Earth pulls down on all masses with an approximate gravitational pull of mass times -10, which is a force field strength, or that's how I teach it. So my force of gravitation, or my weight, is going to be 20 newtons of pulling force down. The mechanical or material strength of the surface, the sandpaper sheet, opposes that and does not allow the block to travel downwards. So these balance, where this force is called a normal force, which just means a pressing force produced when two surfaces are in contact. So you can think of the surface as pressing up onto the bottom of the block, effectively squashing these things together. These balance, which means this block will not levitate or crash through. Because of the nature of the interaction of the surface and the gravitational pull, these are balanced forces. They're equal in size, opposite in direction. They do not form a Newton's law third pair. So they're different things. One's a normal force, one's a gravitational force. Those are there, they're not going to affect the motion, but this does affect the friction. So I've just done my verticals. Now I'm going to look at my horizontals. I'm going to choose things to go to the right just because that's the way traditionally I teach it. So my pulling force is going this way, so I'm just going to say F pull equals 50 newtons. Friction is going to always oppose the initiation or the continuation of motion, so I'm just going to show my FF back this way. I know by default this is going to be negative from a direction standpoint, and that's what I know. Now, if I need to calculate the force of friction, what I've already presented to my students is the fact that the friction equation it's an absolute value equation. It doesn't really give direction, it gives magnitude. So the amount of friction produced between two surfaces is a product of what is the roughness of the surfaces, the coefficient of friction, multiplied by how strongly are these forces being pressed together, which is your normal force. So if I knew these two, I could come up with a value here. But guess what? I don't have the coefficient of friction, so I cannot get to friction directly through a calculation. I can calculate this, which is really my goal, because if I can get to this, I can get to this by using Newton's second law. So this is why I refer to it as a backward style problem, because we're going to have to start with Newton's second law, squeeze out the value for force of friction, and then work backwards to get to the coefficient. So with what I have here, I know that Newton's second law says the acceleration of an object depends on the net force, the sum of all the forces acting on that object, divided by the mass of the object. Now, this traditionally is broken up into, well, what's the acceleration in the x direction and what's the acceleration in the y direction, because we deal with them separately because they're individual. The y forces are going to cancel, so there's no need to look this way. We want to just look here and say, I have two forces. I don't know friction, but that's not going to be a problem because in this equation, we're going to find we only have one unknown. My acceleration is 3 meters per second squared. The two forces in play here are my force of friction. I do not show it as a negative. I just write down, this is the force. The math will tell me if it is negative or not. I'm going to add that vector force, which is horizontal to the left, to a vector force that is horizontal to the right. So that's my 50 newtons. And the mass of this object is 2 kilograms. If I do a cross multiplication here, a kilogram times a meter per second squared produces a newton. It's a mass times an acceleration. So we have 6 newtons over on the left-hand side now, and we have the force of friction, and we have this 50 newton force over here. If we just follow through on the math here, we're going to get 44 newtons is the value of friction that would interact with 50 newtons of force to give me a 6 newton resultant, so to speak. So this is my force of friction. Pretty serious force of friction here. It's fairly large. I need to get to mu. So now I'm just going to use this and solve it in terms of that equation. So my frictional force, now I'm just going to do magnitudes here because this is all about just the size of it, not about the direction. So I just need to know that the fact that we have 44 newtons of friction. And I want to solve for the coefficient, and I know that this depends on the coefficient and the size of the normal force, which is 20 newtons. So if you look at the math here, this is going to be fairly large. 44 newtons over 20 newtons. And right now I can hear my students screaming, going, you told us the mu would never be greater than 1. Well, yeah, I lied to you. Sue me. This is pretty aggressive for sandpaper. Probably way unrealistic. That's my New England coming in there, way wicked. But you're looking at the fact of usually 1 is an upper limit for what you encounter in most everyday objects. So this is going to be a 44 over a 20. And I know guys are out there doing it in their heads right now, or guys and gals are doing it in their heads. I've made enough mistakes. I'm not too proud. My mu value, my coefficient of friction, will turn out to be a value of 2.2. And there is no unit on it. It's just a multiplicative or multiplication or multiplicative factor of how many times the normal force value is the friction. So that's my mu. So in summary, get your free body diagram going. You're going to find that you know the acceleration rate, which is going to encourage you to use Newton's second law as you start the problem solving process. You're going to have one unknown, which will be your frictional force. You can solve for that unknown, knowing everything else. And then once you get that unknown, go one step further and determine what is the value for the coefficient using the friction equation. They're all done the same way. So I hope this doesn't confuse too much. I hope it helps. Have a good night. Bye-bye.